Hi, today I would like to give you some basic information about internal forces in StatiCa connection. My name is Ivan Beleš and I am support engineer for STIA and StatiCa. In this video you will see some basics about how the forces are inputted in StatiCa, how they are transformed for the finite element model, and then about the importing of the forces from Excel, for example, and from another connection, and on the end some tips which I have from the hotline. Now we are in StatiCa connection with a very simple model. First, where we see the forces. You can change how the model is displayed on your screen. There are some buttons. The first one is the axial scheme. And if you are in the axial scheme, then you see the forces, how they are inputted in the model. But they don't act in the node. So you input the forces directly in the node. If you have a finite element analysis software, you can read the forces. These are the forces on the end of the beam in the local coordinate system of the members. This is very important. The coordinate system can be displayed in StatiCa, and here you see also the direction. For example, for n plus, I go in this direction. Y is going in the background of my screen, so the plus my should go in this direction, so against the axis and against the clock. So this is the plus my. So you can see it. We are in my, and you see also my is here, is defined with plus, is here in the member M2. This is the member M2. But the forces cannot act in the node, in the model, because we have one finite element model, and these forces have to be transformed on the end of the model. The end of the model changes. If you input some operations, then the member will be longer. The forces goes with the end of the member. They will be automatically recalculated. You can see it. If you go, for example, how can we see it? We can check, for example, here, we can click on the line with the force, with my bending moment. And then you see this bending moment is transformed on the end of my beam. So on the end of my beam is acting this bending moment my. Why do I do it with this mouse? So this is my, where it really acts. My is very simple. A little bit complicated is it if we have some shear force. Let's define a new load, for example, with the name. For rename, F2 is working. So you can click here, F2, and say, for example, BZ. And then we have some shear force of minus, I don't know, 50 kilonewton. Is going down. So what we see is here this minus 50 kilonewton, but it cannot act here. It must go here. If we move this force here, it would create some bending moment, but we have defined the bending moment is 0. That means we have go here. I will show it in some picture. We have vertical beam, horizontal beam. This is our node. And we have forces. This is my bending moment, my. This bending moment can be simply moved to the end of the beam. This is not an issue. But we have also some shear force, for example, Vz. If we move this shear force, Vz, it would create an additional bending moment. I write delta mz is Vz times R, if the R is the length of my member. But we have told we want to have only this bending moment, which is My. This should act in the node and not My plus Vz times R. Therefore, on the end of the member, we should input another bending moment. I will do it in yellow color, for example, this one. And this is My here minus Vz times R. And this is the bending moment which is inputted automatically in the program on the end of my member. Of course, if you add some openings, for example, then the member will be longer, and this force goes to here, and then the R is also some different value. We have this R, R2 for example, and then we have to start with a different bending moment. So this is done fully automatically. You don't need to care about it, but you have to know that if you want to see this bending moment, which is automatically inputted in my model, for example here in this direction, then you have to go to this axial view and you have to click on this line with the correct member, with the correct forces, and then you see it. For example, we have bending moment of 50 kilonewtons, then we should start with 50 kilonewtons, but we have some shear force and we should reduce this bending moment with our shear force, with this shear force Vz times R. So, and this is then the bending moment which is automatically inputted on the end. Let's click on this member, and then you see there is a support, and if we go to our forces and we input some forces also on this M1, for example on the beginning is, I don't know, is at the top. Let's write 100. Okay, 100, and on the end minus 100. You see this force is red. Why? Because if it will be transformed on the end and we have support, then this force is going to the support, so it's not in the model. Instead of this force, we have the reactions in the support. So also if you input some bending moment, for example 20, and here also 20, then you see they are red, so they are not inputted in the model. During this transformation of the forces from the beginning to the end, if you have a standard 1D member model in your analysis software, then this is only 1D member, you have only one force. But in IDEA StatiCa we have a shell model, so we have to load on the end some plane. So this 1 point load have to be distributed to the full cross section. Let's check it. So we have this shear force, and this shear force must be replaced to all these members, and the bending moment also to this, to the full cross section. For axial force, shear force and bending moment, we get one very rigid plane. So this plane will not deform. We can check it. Do I have calculation? No. I have to run the calculation. I skip the calculation in this video recording. We can go to the check, for example, to equivalent stress, and I would like to see for the load case with the axial force the deformed mesh. And you see, for example, from this side we can make it a little bit bigger. Then this is one plane, and the same also for the shear force, it's one plane, and also for the bending moment. It's each time one plane. Only for torsion, it's not one plane. Reduce it to 10, and you see it's deformed. So for torsion, it's not there, because if it would be forced to one plane, then we would get some additional stresses in the model. So for the warping, it's free. A small tip, maybe you have seen, there is also load in percentage. What does it mean? Idea StatiCa can calculate how much forces can this cross-section take for elastic bending, for example, for the axial force, only for elastic loads and for elastic cross-section properties. And if you activate it, then you can create a new load, for example, axial force of 50%, and then you get one force of 1600 kilonewton. If you want to see it also here, then you can simply put it off and on, and you see the forces in percentage of the elastic capacity of the cross-section. Expect for the torsion. For torsion, you cannot input it, so you have to input manually forces in kilonewton meters. But for shear and bending moment and axial force, it works. So it's good if you try how much can your connection forces take. In our model, the forces act, as I explained on the beginning, directly in the node. But sometimes I will create another connection. Go to this one. Maybe there is some similar, yes, share connection. For example, this one. We'll create this. It's very simple connection. It's already predefined. And if we go to the beam, then you see there is defined that the forces acts in the bolts. And if we go to this axial model, then you see we have defined here that we have zero bending moment for the B. That means the inputted model is zero. So all bending moments which are created are from this transformation of the forces. And usually standard, the bending moment 0 should be here in the node. And this is if you say the forces act in the node. Then we have bending moment 0 in the node. But for such connections, usually you want to have bending moment here, 0, which is 0. So this line of the bending moment should go through this point. And if you use some connections like this fin plate and another, then it's automatically calculated. If you say bolts, then Idea StatiCa knows where are the bolts. It's not possible each time. Sometimes you have some complicated connections, so check it if it's correctly. If not, then you change the position to position, and you can write, for example, 100 millimeter, 150, and then you can check and see where your forces should have the 0 bending moment. If we would have the forces in this point, then we would get here some bending moment, and from this bending moment forces in these bolts, and these forces are very large if the bolts are very close to each other. It's sometimes I have a discussion with customers. They say this is not really correct because we have this 1 millimeter gap between bolt and between the opening in the member, between the hole. But if the member will get deformation, then maybe this 1 millimeter is not enough, and then the forces will be transferred. So you have to be careful, read some literature, there are some articles about it, but usually it's defined that here is a 0 bending moment. Okay, it was the explanation of the forces where they act. sometimes I get such a model on the hotline that there is something wrong with the forces. What happened? You have head plate, which is applied to the column, and then you want to cut this horizontal beam, the B. What the people are doing, if they start with idea StatiCa, usually they move this member B. But you see, if you move it, you not only move the member, you move also the forces. And if we have some shear force, for example, here, then this shear force creates, of course, a bending moment. Then also we move the bending moment, but we should have this bending moment here. So in this case, if you want to do it correctly and you don't want to move the member back, you can say to position 200 millimeter, then you have it back, but then you have some bending moment also on this side. It's not nice if you do it on this way. There is one better option. Simply remove the extension in X, change the position of the forces here. So instead of moving the member, because if you move the member, you move also the forces with the member. Also the eccentricity in Y and Z direction is applied to the forces, so they act in another position. Then it's better you go to the operations, you create this cut operation. I go back to this view, and we want to cut B with C with the bounding box closer, no, the farther, but you see it's not enough. I don't know if this was also in 23, I think this is in 24, a new button, extend the member, and then it's extended, and if you check the forces, then they act correctly in my node, so I don't need to move the forces in one and in opposite direction. So simply extend the member with the operations. Don't move it if it's not necessary, because with the member you move also the forces. There is also a check of equilibrium of the loads. In the node, usually we should have equilibrium. There is one button for it, which was in older versions not activated. Now it's automatically activated. What is this doing? If you activate it, and if you have standard members, which ends in my connection, then there is no difference between loads in equilibrium and not in equilibrium. But for the members with the type continuous, if you have loads in equilibrium, you see there is one support. If you deactivate it, then you have two supports. For member with the type continuous with no equilibrium, you get two supports. What does it mean? If we have a force from here, then it stops in this support. It stops also from here, but this is not my issue. So if you don't care about this member and you want to design only your connection, then it's okay. But if you have also designed, for example, the stresses in this member, then it's important if you have the forces from the member in your calculation or not. Another small difference is if you have the loads in equilibrium, you go to some load case, then you see this table. This is only information for you that you have some unbalanced forces. For example, we have this load case. I have, let's say, create a new load, and we have in M2 axial force of minus 1000. Oh, this is in percentage, sorry. Minus 1000 kilonewton, and then see I have unbalanced forces of 1000 kilonewton in global coordinate system. So I have to create some forces which acts back. I made it worse, minus 500 and minus 500. So, and now I have equilibrium. So you can use this as a small calculator to calculate the equilibrium. Everything which you input in this support will be not included in the calculation because we have support there, so it's not necessary. What is the difference? I go to these forces. You see I have a force in M2 1000, then I have this 500 back, but I also have 2000 kilonewton in both directions. Okay, we don't have it here, but we have it from this side. So if I say loads are in equilibrium, I have only one support. You see it on this red plate. We run the calculation, and after the calculation, we see all stresses from the horizontal, from the forces from the horizontal beam, and also from the forces from the vertical beam from my column. Aha, it's not necessary. I can put them all off and calculate again. It will be quicker. So, of course, so let's check it. Go to the equivalent stress. You see that we have a lot of stress in our column from the axial force. If I go back to the design, deactivate them, then I have support. So this force 2000 is not in my model. It stops at the support, and my column is not loaded with this axial force. And you see also different utilization, and in the check you see also different, you don't see really different stresses, 200, 700, and we have 0.2, and if we go to forces in equilibrium, then we have 2%. So check this. If possible, it should be activated, the loads in equilibrium, and it has only influence on the member of the type continuous. If we are in the loadings, sometimes I get also such models. Somebody has some H section and have to reinforce the flanges. There are two ways how to do it, and they are different. So first, you can simply weld one plate to it. And if you check I have the results, I can go to the check, to the plastic stresses. Then you see the stresses start here in my plate. So I have a part of my model without the plate. So the model on the end has one rigid plane, but this is without my plate. So, and if you have a longer member where the plate goes through the full member, then it's not correct because the forces goes from the top flange then to your reinforced plate, and this is different. Then you go to the cross section. I have another model here created. It's better way, you create a new cross section. So if you are in the member, then you have to use some general cross section. I will create also one video about the cross sections in Idea StatiCa. So I have created one. We can go to it. I have created one EGA 300. Then with this plate, they are glued together, and on the end, both are loaded with the bending moment, for example, and this bending moment is transferred to this one rigid plane, and the full cross section also with the reinforcement is in one plane. So, and this has then different distribution of the loads. Do I have results? No. And then go to the check, and if we look at the forces, then you see, of course, different picture and also different stress distribution. So better if you have the longer member with some reinforced plates, then do it with the cross section. You can also import forces from another connection. One is this important. For example, you are working also with some CAD software, and you get the full model, for example, from Tekla or Advanced Steel. And then you have your analysis software, for example, StatiCa. There you have your node with the members, but without the model, with the forces. So you open the model from Tekla, where you have the full geometry, and you can get the forces from the exported model, for example, from StEngineer, and import the forces in your model where you have the full geometry. So how we can do it? I will save my model in with another name, model, let's say model 1, 2, 3. And okay, then I have the model and model 1, 2, 3. Now I am in model 1, 2, 3. I will delete all loads. So I have some model with my connection without loads. So I can go to connection import, select my model, open it. And then I save from connection 1 and import the forces. And now I have the forces. In this type of import, the name of the load case is important. If you have a load case or this load effect with some identical name already in your model, then the forces are rewritten. So you lose your forces. So you have to rename your load cases if you don't want that IDEA StatiCa will rewrite the forces. So the load case with some name will be replaced on the same load case with the same name. So this is very important. Another way how you can import forces is Excel. Some people prefer it because they can prepare the forces, can select the maximum or so. You can, if you don't know how the Excel should be designed, then simply export your forces into Excel, write test 1, 2, 3, for example, and then we can import. We can check our Excel. This is our Excel, which I have exported. Let's say I want to have another forces. I will delete them. So I will delete it. So, and write a load, for example, I don't know, ultimate limit state 1. And then we have some forces 10, 20, 30, 15, 20, 25, and so on. 50, 50, 50. Okay. Then you have to select this area, including the first column and without this description of the columns. Copy it, go back to IDEA StatiCa, go to Excel import. I don't think you have to select something, simply click Ctrl V and this will be imported. In this import, the names of the load cases are not important. You cannot import the names, so they are each time use these internal names. You have to change it after the import. What you can do is you can select one member and move it to the top, to the bottom. So if in your Excel you have a different sorting of the members, you don't need to change the full Excel because maybe you have, I don't know, 50 load cases. You should then change everything. You can change it here. If you have imported more load cases, then these members will be switched simultaneously, so together in all load cases. So you don't need to go through all load cases only one time. And there are also some extra buttons. Replaced existing loads, then they will be replaced instead of edit or import only extreme values. So now we can import them and then with F2 rename to ultimate limit state 1, for example. So you have to rename it afterwards. Okay, one special thing which I get on the hotline regularly, almost from each customer. Mr. Belej, I have imported from analysis software, and they are not in equilibrium. 99% of the cases is that you have in your analysis software earthquake loads. If you have earthquake loads, then what are the programs doing? The earthquake is usually calculated with the response spectra analysis. We have some simplification, some buildings with 3 stories, mass M1, M2, M3. In the response spectra analysis, the model is split to more eigenshapes. We have the first one, second one, which goes in this and in this direction, for example, so, and the third one, which each one is going in another direction, so, for example, so. This is the frequency 1, frequency 2, frequency 3, okay. For each of these load case, the programs calculates forces. F1, F2, F3. The force is calculated by the mass in the node, for example, mass 3, times acceleration, times this phi 3, and times this participation ratio. Participation ratio is simply a sum of masses times some deformations in the full eigenshape. So then we get forces. Can I delete this? Oh. I didn't define correctly my eraser. So go back to brush. Doesn't matter. From this calculation, we get results. Bending moments, for example, shear force. Here also, bending moments, it goes from this to this direction. And then another which goes to this, and this direction. So then we have M1, for example, in this point, M2, and M3. But we need one force, one bending moment, one shear force. Here also we have shear forces, for example, these types. So, and we have the shear forces goes, I don't know, for example, this type. So then we have VZ, VZ2, VZ3, 1. They are then collected together with combinations SRSS or CQC, square root of sum of squares. I explain only this one. This is simpler. What we are doing, we say M1 squared plus M2 squared plus M3 squared. A square root of them is my bending moment. And from this square root, I get only positive value. That means I have max from My. I have mean from My, because the programs calculated with plus and minus, of course. And then to this My, I have also Vz max, but this is only envelope. So I have envelopes and one sum maximum of bending moment, maximum of shear force, maximum of axial force, and all these maxima. And then in another combination, all these minima will be collected together in one load case. But you don't have equilibrium in these loads. Sometimes I know only C engineer. In C engineer, you can activate these signed results. That means C engineer looks at the most important eigenshapes and reads the signs for the results from this one load, from this one eigenshape, and rewrites it on the results. So then you also will not get 100% equilibrium, but it's better than without it. So this is important. If you have earthquake loads, you will not get equilibrium. And the last one, of course, I have explained it on the beginning. The forces are in the member, if you move the member, if you create some eccentricity in Y and Z direction, also in the X direction, and if you rotate, for example, then all the forces goes with your member. So be careful with these operations. You will not have the equilibrium if you move your members. So I hope it was interesting for you. It was not everything about forces. In the description, I will write also some links to the help Idea Statica, to some articles where you will find some explanations to internal forces. Thank you very much.